Dr. Mark Giese here with Science Moment. Today I'm going to talk about the difference between the probability of a hypothesis being true and the likelihood. We use these words in everyday language in very similar ways, and we don't really distinguish between them, but within mathematical circles, they point to different things that are related, but they're quite different, and they help us get a little bit better handle on the difference between a conspiracy theory or an highly inelegant theory that has far too many parts that are needed to explain the thing that you really need to explain, and not just a theory about conspiracies. We've talked about this before. So the difference between a conspiracy theory and a good hypothesis that explains it with high probability. So when you're interested in how probable is some given hypothesis given the data that we have so far, there are two key things that matter. The first is the likelihood. And that is, what's the probability of getting all the evidence that we've seen thus far if that hypothesis that you're talking about were indeed true, right? So what's the probability of getting all this evidence if that hypothesis is true? And we write this as the probability of the evidence given that hypothesis. Were that hypothesis true, how probably would we get all these data? So that's the likelihood. Now, it's easy to come up, it's not always easy, but there's often many hypotheses such that you can come up with one, or many, that perfectly explain all of the evidence, right? So if you have a bunch of data points and they're bouncing around a straight line, but they're not all on the straight line, well, you can always come up with some kind of polynomial equation, some kind of curvy curve that goes through and hits them all, right? And you've come up with some weird polynomial curvy curve that has lots and lots of parameters. It's like x to the 7th, well, that's like 3x to the 7th plus 4x to the 5th plus 3. And it's some big, long polynomial equation that explains it. And it has high likelihood in the sense that you've rigged it such that that particular curve happens to go exactly through each data point. So very high likelihood. But what have you done? What you've done is that you've just created a really curvy, arbitrary one that happens to fit all of the data. That just means it has high likelihood. And it's obviously a bad hypothesis because there's a much better one. There's the one that just goes right through them all, and it's a little bit, has error. In this particular case, it has a little bit of error in each case, but the idea is that the data themselves have error when you're measuring them, so don't perfectly match reality. And so you have something that's much, much simpler, just a linear hypothesis in this kind of way of talking about things, that explains very well all of the data. Now, it doesn't explain the data as well. It has actually slightly less likelihood because it doesn't perfectly explain the data points like this really curvy one. So that where it benefits, though, is that it has the other thing that matters, which is the prima facie plausibility, or what's called the prior probability of that hypothesis. The linear hypothesis, being so many fewer parameters, is just intrinsically a higher prior probability. It's just intrinsically, in the absence of any information, even before we had any information, it is orders of magnitude more probable, and let's just keep these terms clear, more probable than is the other one. And so these two things balance, and it's the product of these two things that determines which has the whole, probability, the total, which has the highest probability given the evidence so far. This is probability of the hypothesis given the evidence, which is equal to the product of the likelihood times this prior probability. This is called Bayes' formula. And there's also you divide it by something too, but that doesn't really matter for this point. That's just sort of normalizing things out. Now, that's data points in a two-dimensional space and looking at a polynomial versus looking at a straight line. But in a conspiracy theory terms, this comes up. For example, someone just tweeted it was a nice example of this, and they tagged me and Twitter and a bunch of other Team Reality folks, and they said, can you provide anything that this particular, and they're about to present a conspiracy theory, this particular theory doesn't explain? Is there anything that this theory doesn't fit? And it went on, so okay, these people, they invented a virus, and then they chose to leak it at a particular time, and so that it would do this, so that it would lead to the pharma do this, and they sent their goons to control the media to do this. And so they've got like these 18 parameters that are all set and all designed, all rigged, and with 7 or 8 tweet thread to explain all of these things, so it exactly fits all the stuff that happened. Now, I mean, whether it exactly does, let's suppose for the sake of argument, it really has, let's suppose, hit a dozen key qualitative evidence points or data points of what happened over the last 2.5 years. And she goes, so surely this is right, because can you find anything that this particular hypothesis doesn't explain? So that's a great example of a high likelihood hypothesis. But it's only a high likelihood in that you've rigged it. You've just picked, there's always, given the data, some really, really high parameter hypothesis that exactly fits the data, that is really high likelihood. That's not interesting. That usually those high parameter hypotheses that have really high likelihood are exactly the ones with the least prior probability. Understanding these prior probabilities, or this intuitive notion of plausibility, is itself an entire science behind it, and it's often people have strong intuitions about it. That is, scientists who deal with these kinds of things walk in the door and they have these good, if they've got good intuitions and good Occam's razor intuitions, they can just feel where there's more parameters and where there's fewer, where there's more elegant hypotheses, and how they have intrinsically higher prior probability. Dr. Tim Barber and I, in 1998, one of our first papers together, maybe our first paper together, 24 years ago, was on a grand unifying theory of prior probabilities and how you can put foundations upon them so that you can derive the kinds of prior probabilities of higher and lower dimensional spaces, and be able to show why are certain kinds of hypotheses intrinsically higher prior probability compared to others, and sort of a grand unifying explanation of this, and a kind of a solution to what's called the riddle of induction, which I can talk about another time. So that's a deep problem, but I just really want to focus here on just those two things. If you find yourself focusing entirely on how your hypothesis explains all of the data perfectly, well, then from anybody who does math and science, and especially focuses on these sort of foundations probability stuff, you're like, yeah, all that you've done is just rigged yourself a high likelihood hypothesis. And of course, there's always high parameter ones that do that. The key to being a good scientist, the key to being a good thinker generally, is looking for the very elegant hypotheses, the ones that aren't necessarily as high likelihood as that. They don't necessarily perfectly explain all of the data. They pretty well explain all of the data, because the data themselves have uncertainties around them, but they're intrinsically low parameter, they're intrinsically elegant, they're very simple, and that's what makes good thinkers and good scientists and good theorists good theorists. Right? That's the difference. And it's, of course, balancing those two. If it has, great, really high prior probability, but it just has such low likelihood, of course, then that's also a bad hypothesis. The good hypothesis has the right balance of these, such that their product is the highest of all the hypotheses of all. And that was your science moment. These kinds of things, in fact, if you're interested, my first book, The Brain from 25,000 Feet, which is with Kluver, and the publisher, and this was published in 2000-ish. Unfortunately, these are academic publishers rather than these sort of trade books or popular publishers, which are sort of affordable rates. It's probably $150. But that's one of the chapters is on the origin, on the solution to the riddle of induction and understanding prior probabilities and these sorts of issues. But it does not get into conspiracy theories and all that kind of stuff. And of course, get yourself a copy of Dr. Tim Barber and my most recent output, a product of 12 years in the making, highly censored by the mainstream media, as are we, is our book. Go get a copy of it. Support independent researchers.